All right, today we're going to talk about sectors of a circle and introduce you to the concept of a sector, which, again, think along the lines of pizza. The slice of pizza, yesterday we looked at the crust part, the arc length. Today we're going to look at the actual slice itself. And so we have the shaded green area here, which represents the area of a sector. And you can see that the sectors are dependent on their central angle theta. And that central angle theta, based on what we looked at yesterday, can be in radians or it can be in degrees. The larger the central angle, the larger the area of the sector, also the larger the arc length. They all kind of work in proportion to one another. So here we were introducing four new formulas for you today. Yesterday we looked at the conversion factors for radians to degrees and degrees to radians. Now let's take a peek at the arc length and the area of a sector, both of which are proportional. So if we look at the, let's say, arc length of a circle, the arc length s is in relationship to the circumference of the circle, 2 pi r. And the central angle of a circle is in relationship to the entire circle of 360 degrees. So we have these two ratios that once we set equal to each other, we end up with a proportion. And so solving for s in this case, 2 pi r multiplies over to the other side, and we get this equation for arc length when we have theta in degrees. Now the same thing works for areas of a sector. The area of a sector is in proportion to the entire area of the circle, as is central angle relative to 360, and once again multiplying by pi r squared to both sides, we generate this equation for the area sector of a circle. In radians, it looks a little different. So yesterday we were introduced to this equation here, that the arc length of the circle is equal to the radius times the theta. And thinking again, proportionally, if we set up the same type of a situation, but this time with not degrees but in radians, for the area of a sector, we have the following two equations. We have k equal 1/2 r squared theta. And then because of this relationship, that r theta is equal to s, we could take the r theta out of this r squared theta group and make that an rs and get this following equation here. So there's our two equations relative to area of a sector, dependent on whether you knew the theta or if you knew arc length. You would obviously pick one or the other. All right, so four new equations for us. Let's actually go and apply some of these things. So we have the area of a sector with a perimeter of 16 centimeters and an area of 15 centimeters squared. Find the radius and the arc length. So we're going to pull out, we're going to take this little pie shape out of this circle here and understand what we've got working with, what we're working with. We have two radius and we have an arc length, and those three things must make up the perimeter. And we already know that the perimeter, it told us, was 16. Now it also told us, relative to what's on the inside, that k is equal to 15 centimeters squared, and that must be made up of either 1/2 r squared theta or 1/2 rs. Now, which one do we choose? Well, you look at the arc length formula having r and s in it, the area of a sector formula also having r and s in it. Probably want to go set the system up between those two because they have the same unknowns. So we have 16 is equal to 2r plus s, and then we would have 15 is equal to 1/2 rs. All right, so let's go do some solving here. If we, like, for example, chose this equation and solved it for s, we would get that S is equal to 16 minus 2R. And then now, if we substituted 16 minus 2R into our S equation, we would get the following. That 15 is equal to 1/2 R times 16 minus 2R. And now we can go ahead and multiply by 2. We get 30 is equal to 16R minus 2R squared if we distribute everything. So I like to make my leading terms positive. So I'd have 2R squared minus 16R is equal or plus 30 is equal to 0. We can pull out a 2. We get an R squared minus an 8R plus a 15 is equal to 0. And then it looks like we can factor this thing. So we get R minus 3, R minus 5. And then know that our radius has the option of being either a 3 or a 5. So we could have 2 different radius here that give us that value. And so that must mean we're going to create 2 different arc lengths because we're creating 2 different arc values, 2 different area sectors. So knowing that R is equal to 3 or 5, we're going to go plug back in to find S. And probably would make sense to plug into this equation, 16 minus 2R, the one that we rewrote. So for R that's equal to 3, we would have that S is equal to 16 minus 2 times 3, or 16 minus 6, which is 10 centimeters. By the way, these radius would also be centimeters. Don't forget the units. And what if our radius is 5? Well, our arc length should be longer. 16 minus 2 times 5. So that's 16 minus 10. There we go. Sorry, shorter, because we still have the same area, so our arc length needs to be a little shorter. So there are our relationships. We have, for an R value of 3 centimeters, we would create an area of 10 centimeters squared. We could also have a radius of 5 creating an area of 6. So there's our relationship there between what R and S could be for that given sector. All right. Apparent size. This is when you're out, you're going to visit some national park or some monument, and there's, maybe you're in New York City and you're looking at the New York State Building, Empire State Building from afar. Maybe you're at an observation deck somewhere else, and the building looks relatively small depending on how far away you are, or it can be very large if you're close. And this has to do with what is known as apparent size. So how big that object look will depend on the size of the object, but also this angle theta that your eye subtends on the object. So imagine this being your eyeball right here. Here's your eye looking at something, and you're having a situation where you're subtending or capturing your object, however far it is, with some given angle theta here. And if that object is far enough away, or if it's large enough, you can assume that this normally have like an arc that we are considering here, right, for the area of a sector. But if you're far enough away, that arc length is going to be about the same thing as just a linear chord that connects these 2 points of that arc. And they're probably going to be very close. And again, this will depend on how far away you are. So this is known as apparent size. So what we're going to do is we're going to kind of substitute this arc length that we have over here, this guy, and we're going to just look at it as being a chord length, and they're going to be very similar to one another. So that's the concept of apparent size, again, involving arc length, radius, and this theta angle. So let's see how this thing works. So the apparent size of a building is 2 kilometers away. It is 0.05 radians. What is the approximate height of that building? So again, visually what's going on is here's your eyeball, and we're looking at some building that's way far away. Here's our building. And you have this radius and this theta angle that we have, 0.05 radians. And we're 2 kilometers away. So that's a pretty small angle. And what would the height of this building be? Well, if we're looking at using arc length is equal to radius times our theta, then we would say that that would be equal to 2 kilometers times 0.05, which is 0.1 kilometers in height, which is the same thing as about 100 meters. Okay, but let's look at it in a little different way. We talked about how that arc length can be basically the same thing as a chord. So now we're going to look at tweaking this triangle a little bit and kind of considering the idea of this of a right angle here. And we look for the height of the building. We still know I'm 2 kilometers away, and we still have this theta that's equal to 0.05 radians. In this case, we get a first look, although you guys have seen tangent before, but we're going to get the comparison here with what if we, using this right triangle, considered the tangent of theta being the opposite side, which is the h, over the adjacent side, which is the 2 kilometers. And knowing that theta is equal to 0.05, we have tangent of 0.05 over 2. And if we solve this one for h would also equal 0.1 kilometers. Which is the same thing we got up here. So because we're looking at some object that's very far away, this angle that subtends our eye onto the object, that our eye subtends onto the object, is so small, it's as if we can look at this instead of an arc length problem, we can look at this as a right triangle problem. Just simply use the tangent idea. So we're kind of getting a little introduction to the trig that's going to be coming our way here in the next chapter. Speaking in tangents. All right, now we got a bicycle wheel, diameter 24 inches. It's turning, rotating at 33 rotations per minute, and we want to find the distance that a point on the wheel travels in 1 minute. So we're going to arbitrarily assign some point on the wheel. Let's say there's our point on the wheel, and that point, as the wheel spins around, obviously is going to travel some distance. Well, first thing we might want to do is figure out, with a diameter of 24 inches, we can find the circumference of the wheel by circumference equals pi times diameter, or pi times 24. So we have 24 pi inches as a diameter. So that is equivalent to 1 rotation. Is equal to 24 pi diameter. If we're traveling at 33 rotations per minute, find the distance at this point. It's going to travel in that 1 minute time. So we're just going to use some conversion factors here. So let's start out with what we know. We know we're going to have 33 rotations per 1 minute. And we like to keep the minutes variable down in the denominator, but I want to get rid of rotations. And so here's where I'm going to use this relationship. 1 rotation equals 24 pi inches. We know that I want to know inches per minute. So I'm going to say that 24 pi inches over 1 rotation. My rotation units cancel, and now I'm going to get inches per minute. And if we calculated this out, we would have, converting our pi, we can have 1,256.54 inches. Assuming we travel at the same rate, or that object around my wheel travels at the same rate, I'm going to have 1,256.54 inches per minute that object will rotate through. Obviously, if the wheel speeds up or slows down, that's going to be different. But assuming that we maintain the same speed, we would have this distance. And there we go. So using conversion factors, we're going to be doing this kind of thing a lot. And we're just taking ourselves out of rotations per minute into some sort of a distance that we've traveled. We're going to be using those conversion factors a lot. So just remember, it's about canceling units, like a dimensional analysis problem. And there we go. So you guys try those problems, 264, and see how things work out.